recording this because I forgot to record at the beginning of class. But other than that, does anybody have any logistical questions they want to ask? Anything in particular to talk about? No? Does anybody have any fun facts? No? Okay. That's fine. I don't have any fun facts right now. I'm sorry, guys. I'll come prepared next week. Don't worry. I have on this slide listed all of the office hours before exam 2. I will add in additional extra office hours that week of exam 2. I don't have those in yet just because I'm not entirely certain about what my schedule will be 2 weeks from now. But our next exam is on the 26th, which is good. We got a reasonable amount of time. Today's the 8th. So what is that? 18 days, if I can do math. So that's a good amount of time. We have lots of available time to do studying, so that's good. So with that being said, if nobody else has any questions, we're gonna get started with really breaking down SN1. So we talked about SN2 last week. What does SN2 stand for?
I know the S stands for substitution, and then the 2 is saying that it's second order, and then the N is for nucleophilic.
Yeah, perfect. So it's substitution with a nucleophile that's second order. With SN1, we see something very similar, except for SN1 is actually a first order reaction. So what that means is it means that the rate determining step is unimolecular, or that only one thing will exist in the rate determining step. So with SN1, another important thing we have to consider is the fact that SN1 is a two-step mechanism. So this falls at contrast to SN2 because SN2 is concerted. It's going to occur in a single step. So SN1 exists in these two steps. In the first step, we have a carbocation form. And in the second step, we have the nucleophile attack. So of these two steps, which one is the rate determining step? The first one. Why is the first one the rate determining step? Yeah, so you definitely said a lot of very relevant information there. The first step, step 1, is our rate determining step. So we're gonna go ahead and circle that. Step 1 is our rate determining step. And what that really means is that this is going to be the step that determines the rate of the reaction. Step 1 is the rate determining step because it is the slow step. It is unfavorable to form a carbocation. And then additionally, we know that this is going to be, if we're looking at an energy coordinate diagram, going to have the highest associated transition state energy. It's going to be associated with the highest peak. So why is forming a carbocation unfavorable? Are carbocations stable? No, they are super unstable. If we look at a carbocation, we know that carbocations have 3 bonds and then an empty p orbital. So there's only 6 electrons. We know that molecules like to have 8 electrons. So we know that carbocations are unstable. Speaking in terms of the stability of carbocations, just for review, what kind of things can stabilize a carbocation? Can anything stabilize it? Is it just hopeless? Hyperconjugation. Hyperconjugation we talked about in terms of radicals. Hyperconjugation can always stabilize electron deficient atoms. So if we look at this molecule right here, we see that there's going to be adjacent carbon-hydrogen bonds. In particular, 1 carbon-hydrogen bond on each of the adjacent carbons. are going to be able to interact with this p orbital, and we do see stabilization by hyperconjugation. Is hyperconjugation the only thing that can stabilize a carbocation? What else can? So not I mean, arguably, a nucleophile will stabilize it. But in terms of like the carbocation existing by itself, in addition to hyperconjugation, you can get stabilization from resonance or conjugation. Resonance or conjugation can stabilize our carbocation. So if we had something like this, an allylic carbocation, we see that we have this conjugated network, and thus those pi electrons will donate some electron density to the carbocation and thus stabilize it. So that's a lot of just fun facts about carbocations. How do we feel about that? Anybody have any questions so far? Okay.
Wait, can you explain again why the first step is the rate determining one?
Yeah, so the first step is the rate determining step because it's going to be the slowest step. It is the least favorable step. In other words, in this case, it's going to be the endothermic step. It's going to be the step that requires energy. Okay, perfect. So then I keep saying that SN1 is a two-step reaction, but I have 3 steps listed on the slide. So why is there a third step? Yes. So if we have a neutralization step, like we do here with step 3, what happens is it's not actually part of the SN1 mechanism, but it is going to exist just to neutralize the charges. Overall, we like to have neutral products. I don't really know why. It's just like something that we like to do. Okay. So then what we're going to do is we're going to get into a little bit more with SN1 with this example right here. So what this question is asking is which mechanism, SN1 versus SN2, occurs in each of the following reactions. Then we want to give the major product and talk about what type of solvent will maximize the rate of the reaction. So with this problem right here, we're really going to want to get into the differences between SN1 and SN2. So let's say we're trying to figure out if SN1 versus SN2 is happening in this reaction. How do we do that? Are there any kind of like tricks, any kind of themes that we can look for, anything to figure out what's happening? Yeah. So having a strong versus a weak nucleophile can definitely give us insight. So let's put down nucleophile strength. But what would that tell us? If we have a strong nucleophile, what does that mean? Yep, SN2, which means that a weak nucleophile would be SN1. Is there anything else that we can use to kind of differentiate SN1 and SN2? I'm really happy that you said that, but no. So the thing about the solvent is the solvent will not dictate what reaction will take place. So let's say we have, so first of all, why did you say the solvent? What was your thought process there? Yeah, absolutely perfect. So you guys learned in your nucleophilicity lecture that if you have a SN2 reaction, it's better to have a polar aprotic solvent. Whereas SN1, it's easier to have a polar protic solvent. Now, this does not mean that every time you have SN2 2, you have to have an aprotic solvent. It just means that having an aprotic solvent will increase the rate of an SN2 reaction. So this is definitely something that is tricky, but solvent will not dictate the mechanism ever. So not quite solvent, but there's one other thing that can dictate what reaction mechanism happens. Yeah? Perfect. So the other thing that's going to dictate what reaction happens is the substitution of the alpha carbon. So does anybody want to elaborate on that?
Don't you look at bulky versus like if it's third degree, it'd be SN1.
Yeah, perfect. So if we have, yeah, so if we have tertiary, it's going to be SN1. If we have methyl or primary, it's going to be SN2. And then the unfortunate thing with this technique is if we have secondary, we don't know. Well, that's really unfortunate. You can't see everything. I don't know why that is, and I don't know how to fix that. So we're just going to erase this, and then we'll write it on the side. So if it's secondary, we don't know what is happening there. So with this particular problem, if we look at what's going on, the very first thing that we're going to want to do is we're going to want to identify the nucleophile and the electrophile. Does anybody have any ideas? Yeah? So why do you think that's the, why do you say that's a good leaving group? Yeah, perfect. That's excellent. So the reasoning was that if a leaving group looks like sulfuric acid, it will be a good leaving group. And that's definitely true. So in case anybody doesn't know what sulfuric acid is, that's H2SO4. So in particular, we want to think about the conjugate base of sulfuric acid. In terms of the fact that this is going to be very heavily resonance stabilized. And that's why that's why we have this logic, is because that conjugate base of sulfuric acid is very resonance stabilized. And if we have something that looks similar to that, it will also be resonance stabilized. So I can redraw my electrophile. So that way you can see, oh, that was a horrible triangle. Wow. So that way we can look at this with a little bit more detail. So we're going to have this oxygen bound to a sulfur. We're going to have double bond oxygens and CH3. So this right here is the full structure of my electrophile. So that is going to be a good leaving group. Definitely going to be a better leaving group than that alcohol, than that OH, because OH is just a bad leaving group. So so does anybody have any questions on differentiating between the electrophile and the nucleophile, or do we feel good about that? Okay, so then next up, let's look at what mechanism is at play here. The first thing I always look at is the substitution of the alpha carbon, and in this case, it's secondary, which is sad, because that doesn't give us any information. So we're going to have to look at the nucleophile. What do you guys think of the strength of this nucleophile? Is this a good nucleophile? Is this a crappy nucleophile? What do we got going on here? So it's actually going to be a weak nucleophile. So this is a weak nucleophile, and that's because alcohols are always going to be weak nucleophiles. So I know that in the lecture video, Axelson mentioned that a lot of times with SN1, you'll use like an alcohol solvent, and the solvent will act as a nucleophile. That's something that could definitely happen here. So we have this weak nucleophile. So because we have a weak nucleophile, we know that it's definitely going to be SN1. which means that it would favor having a protic solvent. This does not mean that it must have a protic solvent. It just means that it would favor having a protic solvent. Okay, do we feel good about this so far? Yeah.
I'm sorry, can you repeat that? You said that, a lot of the times that the nucleophile with an alcohol will have to, solvent.
Yeah, okay. So what happens is, so alcohols in general are just really common solvents in organic chemistry. And if you have, if you want to perform SN1 with an alcohol, you can oftentimes use that alcohol as the solvent. And then the solvent can act as the nucleophile as well.
Oh, okay, cool. Okay, thank you.
Okay, so we know that this is definitely going to be SN1. So now what we want to do is I'm going to erase all of these lovely drawings, and we're going to go over the mechanism. But very first, before we do that, we're just going to do a brief overview of SN2 because we want to have those ideas in our mind. We want to be comparing and contrasting this whole time. So I'm just going to draw a generic SN2 reaction. And we know with SN2 is going to happen in a single step. It's going to happen in a single concerted step. So what's going to happen in the same step, we're going to have the nucleophile attack the alpha carbon and my leaving group is going to leave. And what's going to happen is we're going to generate a product that displays an inversion of stereochemistry. So this all happens in a single concerted step. So with SN2, does anybody remember what the HOMO is, or what the HOMO, or could anybody tell me what the HOMO is for this reaction? Say that one more time. I'm sorry. Perfect, perfect. So the HOMO for SN2 is always going to be the lone pair in some hybrid orbital. We don't know the hybridization of this nucleophile, but a lone pair in the hybrid orbital of the nucleophile. So more broadly, remember the HOMO is always going to be the lone pair that does the attacking. Now, what about the LUMO? What's the LUMO for this reaction? Beautiful. So the LUMO is going to be the sigma star antibonding orbital for the carbon bromine bond. So remember, the LUMO is always going to be the empty orbital that the nucleophile attacks. So let's kind of compare that to what's happening with SN2, or with SN1, excuse me. So with SN1, we know that this reaction is going to take place in 2 steps. What's the first step? Yeah, and that leaving group is just going to fall off. What's going to happen is the electrons from this carbon leaving group bond are going to be pushed onto the oxygen. And as a result, what's going to happen is we're going to generate a carbocation. That looks like this guy right here. And additionally, we're going to have that leaving group that's going to be resonance stabilized. And then we'll still also have our nucleophile in solution. So, yeah.
So the SN1 only forms the carbocation because there's 2 different steps, because the leaving group leaving and the nucleophile attaching is 2 separate steps.
Yes. So SN1 will always form a carbocation, and it forms that carbocation because there are 2 distinct steps. The leaving group falls off initially, and then the nucleophile comes in and attacks. So then that definitely tells us what's going to happen in our next step. We're going to have our nucleophile come in and it's going to attack. Now, the important thing to think about here is what is the hybridization of a carbocation? It's sp2, right? So that means that a carbocation is going to be flat. It's going to be planar, which means that when the nucleophile comes in and attacks, it can either attack the back side or the front side. So what we have to consider is that we're going to generate a racemic mixture of products with an SN1 reaction. Does that logic make sense to everyone? Does anybody have any questions on that? Okay, this is getting a little bit too smushed. Let's draw this over to this side. Now, similarly to what we talked about with SN2, we only will generate a racemic mixture if our alpha carbon is a stereocenter. So if the alpha carbon is not a stereocenter, you can't have a racemic mixture of stereoisomers just because you don't have any stereoisomers that exist. Does that make sense to everyone? Mm-hmm. Yeah, so when we say like racemic mixture, a racemic mixture is the same thing as a racemate. They're just like two different words to describe the same thing. So what a racemic mixture means is that we'll have basically a 50-50 sample of both of these two molecules right here. Then what's going to happen is, so this right here, this is our 2 steps of our SN1 mechanism. But because we do have that charged product, we are going to have an additional acid-base step where we're going to have some molecule come in and deprotonate. We can have the solvent deprotonate. We can have the leaving group deprotonate. Let's say in this case, our solvent is water. We can have that water come in and deprotonate. And that will give us our final products. All right, does anybody have any questions on that? Does that make sense? Yeah. Yeah, so the leaving group can also deprotonate. You can have either the leaving group or the solvent come in. And you can really just choose whatever one you want. Like there's not like one answer that is more right than the other, because remember all of this is happening in like one reaction flask. So you really don't it can be either one. You don't know which one will be more likely or anything like that. It'll just be whatever's closest. So, does anybody else have any questions about that mechanism? There's only one more thing that we're going to talk about then at the beginning of class, and that's going to be what the HOMO and the LUMO for this reaction is. So does anybody want to give it a shot? Yes. So the HOMO is going to be, the HOMO always is going to be the electrons that do the attacking. So that's always true, is that the HOMO is always the electrons that attack. So in this case, it's going to be this lone pair right here, because that's where I drew the arrow from. So it's going to be the sp3 lone pair on the oxygen of the nucleophile. What about the LUMO? The LUMO is always the empty orbital that is attacked. What's going to be the empty orbital in this case? Beautiful. So the LUMO is going to be that empty p orbital of the carbocation. So how do we feel about that? Does anybody have any questions in regards to that? Does this make sense? Do you know everything about SN1 now? Probably, right? That's how it works. All right, so then what we're gonna do at this point is I'm gonna go ahead. Does someone on Zoom have a question? Are we good?
Good.
Okay, sounds good. So what we're gonna go ahead and do, and I'm gonna go ahead and stop sharing my screen, and I'll put the people on Zoom into breakout rooms, and I'll put out the worksheets for people in person to go ahead and grab. I sent out the Google form for class today, about 2 hours ago, to all of your guys' emails. So if you want to go ahead and fill that out now while you're waiting, that would be perfect. Also, there are a lot of people that aren't attending in person today, so I have a million worksheets, I think. So if you guys want to take extras, or if you know anybody that will use them, please take them away from me. That would be excellent.